When I tap the rod, I excite bending vibrations in the rod, which in turn will excite sound waves that propagates through the air to the microphone that records this. In a vibroacoustic system like this, the tapping force is the excitation or source. The sound pressure at the microphone is the response or receiver. And the bending vibrations followed by the radiated sound waves is the transmission path between the source and the receiver. Now, what will happen if I hit twice as hard? Well, the response, the sound pressure at the microphone, will also increase a factor 2. How come? Well, the reason is that in practice, most vibroacoustic systems can be approximated as linear systems. And a very, very useful property of a linear system is the homogeneity or proportionality principle, saying that if I change the excitation a factor of alpha, its response will also change a factor alpha. This means that if I know how the excitation is changed, I can, without complicated calculations, predict how its response is changed. And that is very, very useful in practice. And this and some other useful properties of linear system we will discuss in this presentation.
So, as we heard before, the linearity assumption is very, very common in acoustics and vibration. So one can then ask, what is a linear system? And from mathematics, we know that the linear function is defined like this. So we have a function y and the variable x. And the relation between these two is a proportionality factor k and a constant term L. So in acoustics and vibration, a linear system can be represented like this. So now we have a parameter, frequency. So all functions and variables here are and factors are frequency dependent. So x here represents the excitation and y the response. And k is a frequency-dependent proportionality factor. Now, in acoustics and vibration, and also electrical engineering, this k here is also known as the frequency response function of the system. FRF is a short form. So one important property of a linear system is, like we saw in the introduction, the homogeneity or proportionality principle. And in mathematical terms, you can express this as follows. So if we can suppose that the linear system response to an excitation F is P, then linearity or this homogeneity principle means that the response to an excitation alpha times the excitation, the original excitation F, is alpha times the original response P. For example, if we have, let's say we have a machine that vibrates, and that machine is standing, it's mounting on the floor. So it excites, when it's running, it excites floor and wall vibrations in a neighboring room. And these vibrations, of course, will radiate sound waves in the neighboring room. So if we now install a vibration isolation system between the machine and the floor, and by this installation, we can reduce the force that excites the floor with a factor 2. Then, if the system can be approximated as linear, we know that the sound pressure that is caused by this force will also be reduced a factor of 2. So this is very, very useful information. A second useful property is what is called the superposition principle. And in mathematical terms, we can express it like this. So if we have two components of the excitation force, one F1 and one F2, and we know that F1 causes the response P1 and F2 causes the system response P2. Then, if we have these two excitations times alpha and times beta acting at the same time, simultaneously on the system, then we can say, due to the superposition principle, that the response will be alpha times P1 plus beta times P2. And the good thing with this is that we can analyze one term at a time in isolation, and then afterwards sum them to the total response. So that is the usefulness of the superposition principle. It makes the analysis much simpler. The third very, very useful property is the so-called frequency conservation principle. And that means that the response cannot have components at other frequencies than the excitation. So if we have a single frequency excitation, for instance at 150 Hertz, then we can only have response at 150 Hertz. So no other frequencies can appear in the response. If it does, then we have a nonlinear system or other sources that contribute to the response. So, as we said before, in acoustics and vibration systems, they are very often approximated as linear systems. So then one can ask oneself, when can we assume linearity without introducing large approximations error due to this assumption? Well, there are two conditions that should be satisfied. First of all, the oscillation amplitudes must be so small that the constitutive material relations are linear. That means, for instance, that for a solid material, Hooke's linear law, the relation between force and displacement must be linear. Secondly, the oscillation amplitudes should be so small that the kinematic relations are linear or can be assumed approximated as linear. So one example illustrating the second condition is the pendulum. If we have a mass suspended in a string like this with string length L, and then let this pendulum swing around its resting position here, and write the governing equation of motion will, if we derive this governing equation of motion, it will read like this. As you can see, this differential equation is nonlinear in phi, in the angle phi here. The sine here is a nonlinear function. But if the angle here, phi, is small, if the oscillation here is small, then we can expand this sine phi in a Maclaurin series. And if we take only the first term in this Maclaurin series, then we can linearize this nonlinear equation of motion to this shape. And now we have a linear governing equation, and the system, this system with small oscillation amplitudes, is approximately a linear system. And the same goes for many other types of acoustic and vibration systems. Beam vibrations, beam bending vibrations. If the beam bending displacements are small, then we can approximate the governing equation as a linear differential equation, and the system will be linear. So back now to frequency response functions again. So we have now, as I said before, there are many types of frequency response functions in vibrations and acoustics. And here are some examples. If we have the excitation in form of a force, and if we have the response in the form of acceleration, then the frequency response function between the force, exciting force, and the responding acceleration is denoted accelerance, A. Meters per second square over Newton is the unit. Velocity, if the response is velocity, then we have the mobility, denoted Y. And if you have displacement, a displacement response, then it's the receptance. If we take an acoustical example, if we have, for instance, an excitation, let's say we study a plate, vibrating plate, and measure or calculate the vibration velocity of the plate, then if the plate radiates sound and we measure the response close to the plate in terms of the sound pressure, then the ratio between the sound pressure and vibration velocity is the acoustic radiation impedance, Z, in pascals per meter per square, meter per second. And this list can be made much, much longer. The frequency response function can be determined in several ways. You can measure it, and you can also calculate it or derive it from, in a theoretical way, from the governing equations. This is one example. So consider this single degree of freedom system where we have an excitation force and we have a responding displacement of the mass m here. So this force can, for instance, be caused by internal processes in the machine, unbalanced forces of rotating shafts, for instance. So the governing equations now for the mass, we have Newton's law. Mass times acceleration equals the net force. And the net force then is the difference between the exciting force here and the force created by the spring damper system here in this cut here. And the spring damper force, this one, is determined by first of all, the deformation velocity of the spring damper system, the t here, and also the deformation itself, z. So kappa here is the spring constant, and dv here is the damping constant. So using these two, you can derive the governing equation of motion, and it comes out like this. And as you know now from a previous presentation, we prefer to work with complex quantities or Fourier transform, meaning that the time derivatives here is replaced with a multiplication with I omega, like this. So this equation of motion then transforms to this equation. And here we have the relation between the complex displacement, Z, and the complex excitation force. So we simply have to take the ratio of these two. Then we have the frequency response function that we want to determine. Z over F, so it's simply this. And as you can see, it's a function of the angular frequency omega, or if you prefer, the frequency F, the circular frequency F. Another example for the same, well, almost the same system is if we instead use the displacement Z0 here as the source, excitation source, and like before, the displacement of the mass Z here as the response. Then the governing equations are almost identical. The only new thing here is that Z0 here is not equal to Z0 anymore, but we have to insert Z0 here. And if you use these two equations, then the equation of motion will read like this. And if we then take the frequency response function between the response Z and the excitation Z0 here, we end up with this ratio. And as you can see here, the only difference here is this numerator, I dV times omega plus the kappa, the spring constant. So these two frequency response functions will later on in the course be shown to be useful in many situations. So remember to use them whenever you can. So if we now plot this frequency response function, as you saw before, it's complex valued because you have this imaginary unit, I here, the square root of -1. So if we plot this in a diagram, it's actually two plots, either the real part and the imaginary part of the frequency response function, or, as we prefer in physics or acoustics or vibrations, the magnitude versus frequency, and phase angle versus frequency. And as you can see here, the magnitude has a local maximum at a specific frequency here. And this local maximum, the position of it along the frequency axis, is known as the resonance frequency of the system. And as you know, well, or as you can understand from this plot, where you have a large magnitude, large size frequency response function, that means if you have a local maxima of the system's frequency response function, it means that the system is particularly sensitive to excitations that has frequencies close to this frequency, the resonance frequency. So if you want to avoid large amplitude responses, then you shall make sure that your excitations does not contain frequencies close to these resonance frequencies of the system. If it does, then you will have problems. So, finally, one alternative way to view a frequency response function is as a part of a source path receiver system. Take this ship, for instance. We have the source here, the drive line, the engine, transmission, and the propeller. And we have the receiver. It could be, for instance, sound pressure in some cabin here. So if we express now this system here, this vibroacoustic system, as a linear system, we have the source, that is the forces here caused by the driveline, and that excites vibrations in the ship hull or the connections to the ship hull. We have the path between the sources and the receiver in the cabin here. And this path here is then, of course, the frequency response function between the force, exciting force, and the sound pressure in the cabins. And we have the receiver, the sound pressure in the cabin. So this is another very, very useful way to view a frequency response function as the path in a source path receiver system. And that's all for now. Continuation will follow.